Hello, Algebra 2 students. Today we're going to continue section 8.3, Logarithms of Logarithmic Functions. Graphing logarithmic functions. The function y equals log base b of x, where b is not equal to 1, is called a logarithmic function. The graph of f of x equals log base b of x represents a parent graph of the logarithmic functions. Properties of the parent function are described in the following table. So the parent function of log functions, f of x equals log base b of x, has five properties. The function is continuous and 1 to 1. The domain is the set of all positive real numbers. The y-axis is an asymptote of the graph. The range is the set of all real numbers. The graph contains the point 1, 0. And as we'll also see in a little bit, the graphs of log functions can be transformed by changing the value of the constants a, h, and k in the equation f of x equals a times log base b of x minus h plus k. There's a lot of interesting connections that can be made to the inverse function, which I'll go ahead and highlight again here as such. The inverse of f of x, which I'll write as f inverse of x, can be denoted as such. So a times b to the x minus h plus k. Now that is a very kind of general form of the inverse of that function, but it's still worth noting, and we've discussed it. For example, graph f of x equals negative 3 log base 10 of x minus 2 plus 1. This is a transformation of the graph of f of x equals log base 10 of x. Now log base 10 of x, I'm going to go ahead and graph using a separate parent function setup. So y equals log base 10 of x. Let's think about this for a moment, which I'm going to go ahead and actually rewrite as y equals log base 10 of x. Essentially this means that we're taking, if you recall, 10 is our base, raised to the y power, and that equals x. So if you think about all the numbers that we can and cannot take the log of, but in turn we're trying to ask ourselves 10 to what power equals that number, we can think about things like, or numbers like, we'll say maybe 10. We can even use 1/10. I like 1/10 in particular. I'm going to move 10 down just a touch. Let's actually call that our third of 3 points. I like 1, and I like 1/10. Now if you notice here, I picked 1/10, 1, and 10, and 1/10 and 10 in particular have obviously the same number, but one is the reciprocal of the other. Well, 1 in the middle there is, well, a number you can always essentially figure out the log of, and I'll explain. So remember, these are all the x's that we're assessing. So 10 to what power is 1/10, 10 to what power is 1, and 10 to what power is 10. So again, I already know my x's, 1/10, 1, and 10. Now I actually figured those out for you, or I came up with those, but in general, as a rule of thumb, 1/10, 1, and 10, or the reciprocal of the base, the number 1 and the base itself are always smart to use because, as you'll find out here in a second, y equals, for the first equation, well, 10 to the negative first is 1/10. For the next equation, 10 to the what is 1? Well, we know 10 to the 0 is 1, and for the last, 10 to the first is 10. So now our respective y's will be negative 1, 0, and 1, which isn't a whole lot more surprising than you could imagine, because if you recall the basic inverse function, which I'm going to go ahead and highlight as such, the inverse of the log function that we note as such, log base 10 of x, is just y equals 10 to the x. And when we make an xy table for this type of graph and function, we pick negative 1, typically 0 and 1. When you plug in negative 1, you get a 10th. When you plug in 0, you get 1. When you plug in 1, you get 10. So simply switching the x's and the y's gives us that particular xy table in red. So I'm just essentially assessing what the inverse function and its parent function, respectively, or parent functions, would look like. So if I were to plot the ordered pair 1/10 comma negative 1, and it looks like we're going up by, interestingly enough here, we're going up by 2.5, which is fine. We'll make do here. So 1/10 comma negative 1, 1, 0, and then 10 comma 1. Okay, so that function takes shape accordingly. Let's all draw that. Now I actually drew it in such a manner where you don't have your x values ever technically touching nor crossing the asymptote, which I'll highlight here as x equals 0. There is a vertical asymptote at x equals 0 for this parent function. Now the function at hand, there are 4 bullets to take a look at, of which I'm going to go ahead and make an xy table, or x, let's say f of x table, just to differentiate a little bit, and make an assessment here. So the x minus 2 is usually where I like to start, although that's the 3rd bullet. That's going to be a shift 2 to the right. So instead of picking 1/10, we'll add 2. We'll come up with that number in a moment. Same with 1, but add 2. That's easier to figure out. And then, of course, 10 plus 2. So that'll be easy enough. So those values, particularly, we know will essentially turn into, and I'll just do the math here, this ends up being 1/10 plus 2, or 1/10 plus 20/10, so 21/10, 3, and 12. So these 3 numbers are smart, because then when you plug in, and I kind of break this up here, 21/10 minus 20/10 is 1/10. Log base 10 of 1/10, as we know from the inverse, from the parent function, which we did use the inverse to essentially kind of help us with, is -1. -1 times -3 is 3, plus 1 then is 4. If you plug in 3 minus 2, that's 1. Log base 10 of 1, again, we know that's 0 from back here. Times anything is 0, plus 1 is 1. And then lastly, 12 minus 2, that's 10. Log base 10 of 10 is 1. Times -3 is -3, plus 1 is -2. So if you guys do the rest of this, noting that, well, the first bullet noted a, the absolute value of which equals 3, if you look at that particular value, you know that it expands vertically, they say, or I like to use the word stretch, or even compress is fine. When a is less than 0, that's reflected across the x-axis, so we're looking at the sign there. And then really last but not least, the 1 here is telling us that it's shifted up 1 unit. And I didn't highlight this, but I'll do that as well. So there are 4 transformations, and then the black curve that you see here, which I probably will need to finish with graphing, 21/10 is roughly about right here. That's an ordered pair, let's say here. 21/10 comma 4, 3 comma 1, and then lastly 12 -2. Okay, so you've got your curve through those 3 points, and that's pretty much it. To continue here, we'll take a look at the graphs of some functions, and what would be wise for us to take a look at is the parent function for each. So when we go ahead and assess the parent function for the first being simply log base 2 of x, for the second log base 3 of x, and for the third log base 4 of x. Okay. Now we'll probably have the time here to do at least one of these in our video today. I'm going to go ahead and pick probably the most challenging though. I'll pick number 3. Number 3 has, it looks like 1, 2, 3 transformations. And what I'll do in assessing those transformations is kind of start with the premise that, well, the transformations are predicated on what a parent function entails or looks like. Again, we'll pick numbers like 1/4, 1, and 4. Log base 4 of 1/4 is -1. Log base 4 of 1 is 0. And log base 4 of 4 is 1. Not surprisingly, look at the y values. If you think about the inverse of this function really quickly here, y equals 4 to the x power. 4 to the negative first is 1/4. 4 to the 0 is 1, and 4 to the first is 4. But again, we're talking about a log function. The log function that we see, y equals log base 4 of x, takes shape as 1/4 comma -1, 1 comma 0, 4 comma 1. There is a vertical asymptote. The idea here with any vertical asymptote in a log function is all of them have a vertical asymptote, not a horizontal, is that you cannot take the log of negative nor 0. So there's your log function. As far as the graph at hand, the one that we want to essentially finish with, because yes, the transformed function takes shape accordingly. So x and f of x. We'll start with the x plus 3. That plus 3 entails us shifting it left 3, but from 1/4. So we'll do 1/4 minus 3. We'll do then 1 minus 3, and then 4 minus 3. Now again, I'm kind of doing it like I did the last problem, wherein I'll just now need to do the math. So 1/4 minus 3, or 12/4, because 4/4 times 3 is 12/4. 1/4 minus 12/4 is negative 11/4. 1 minus 3 is negative 2, and 4 minus 3 is 1. If I pick these three numbers, the rest should be pretty straightforward. If I plug in negative 11/4, negative 11/4 plus 3, which is 12/4, that's 1/4. Log base 4 of a fourth is negative 1. Times 2 is negative 2, minus 2 is negative 4. Plug in negative 2. Negative 2 plus 3, that's 1. Log base 4 of 1 is 0. Times anything is 0, minus 2, minus 2. Lastly, plug in 1. 1 plus 3 is 4. Log base 4 of 4 is 1. Times 2 is 2, minus 2 is 0. So here we go with our transformed graph, which basically, again, if you think about it, was left 3 from just looking at the equation. Left 3, vertical stretch of 2. Let's write those down. Vertical stretch, thanks to the a value of 2 in the front. And then lastly, it should be a shift down 2. So let's take a look. We're going to compare the red and the blue here at the end. Negative 11/4, common negative 4. So that should be roughly about here, let's say. Close enough. Negative 11/4, common negative 4. Negative 2, negative 2. And then lastly, 1, 0. And that is interesting how they actually share a point there, which is totally legitimate. We can definitely have that. I'm going to draw my vertical asymptote now at x equals negative 3. It's not surprising that we have a new vertical asymptote because we shifted it to the left 3 units. So x equals negative 3. You graph your function through your 3 points, and that is your final answer. Again, the red function shifted left 3, vertically stretched by 2, and then down 2. So that speaks to your final graph. Now, with the time that I have remaining, I'd like to take a look at some questions on page 21. Particularly anytime you guys are asked to convert or write each equation in exponential. So like number 1, keep in mind this is your base raised to that power. On the right side, that equals 243. On a problem like number 7, we'll jump here. Writing each equation logarithmic, if we start with an exponential, 8 is your base, so now log base 8. And the number that we are taking the log of is 1 over 64, and that should then equal negative 2. And that's it for that particular problem. And then we go ahead and move on to problems where we're evaluating. Things like, I'll jump to 13, for example. 4 is your base, so 4. Now we're rewriting this. I'll write a equals what kind of there to help us think about this. 4 to what power is 1 over 64. So that's the exponential version of this. Well, we already know that 4 to the third is 64, but that's not the answer, right? Because we want to note it as 1 over that number. So 1 over 64 requires what? An exponent that's negative and not positive. In kind of a similar sense, using some fraction analysis, let's look at number 16, 27 being the base. To what power is 1/3? Okay, this one's a little bit different, right? Because our base happens to be bigger than the denominator by itself. If we just looked at the reciprocal of a third, 27 is bigger than that. We could still do this, though. And we could do this considering the fact that 27 happens to be a perfect cube. Noting this, we can say that 27 to the 1/3 power is in fact 3. But let's be careful. 27 to the 1/3 power, yes, that's 3, but we don't want 3, we want 1/3. So what if we made it negative 1/3? Okay, think about that for a moment. A little bit harder question. This is really us saying 1 over 27 to the 1/3, the cube root of which, again, we should know, looks something like this. And the answer is, of course, at least checking-wise, is a third. So the answer to this question is actually negative 1/3, the exponent. Tomorrow we will conclude with more questions, taking a look at some more graphs, but that should be it for today. complete your homework.